So what is a polynomial inequality? Well, if f of x is a polynomial function, then a polynomial inequality has the general form. And there's 5 general forms. So we have, for the first one, f of x is strictly less than 0. F of x is less than or equal to 0. F of x cannot equal 0. F of x is strictly greater than 0. Or finally, f of x is greater than or equal to 0. Now, the real zeros of the polynomial function divides the x-axis into intervals where f of x is entirely positive or negative. So to further explain this sentence we've just said here, we have a graph of some function f of x, and the first thing to know is where the real zeros are. So I've just highlighted them there for you. You can see that's where x equals -4, -2, 2, and 5. And if you look at this graph now, starting from the left-hand side, this section that I've highlighted in blue, you can see lies above the x-axis. So f of x here is entirely positive. And then between -4 and -2, this section that I've highlighted in red, which lies below the x-axis, this is where f of x is entirely negative. And then between -2 and 2, we can see f of x is entirely positive. And then between 2 and 5, we can see f of x is entirely negative. And because the last section here lies below the x-axis, we can see f of x here is also entirely negative. So what we see here is that the real zeros have divided the x-axis into intervals where f of x is entirely positive, and we can see that in the blue sections, or f of x is entirely negative, which you can see in the red sections below the x-axis. So the graph you can see here does make it a lot easier to see where f of x is negative or positive. However, it can be quite time consuming to make every single time we want to solve a polynomial inequality. So what we produce instead is what we call a sign chart for f of x. So we'll show you as follows. So we have the x-axis, and the first thing we want to input is our real zeros. So this is where x equals -4, -2, 2, and 5. And then we'll use what we call test values. Now these are x values which we substitute into f of x to see if it gives us a positive or a negative value. So if I was to pick a value of x here, which is less than -4, and substitute into f of x, I'd end up with a positive number, and I indicate that with a positive sign for this interval. And I do the same for each interval throughout. So over here, I'd end up with a negative sign, a positive sign, a negative sign, and another negative sign there. And you can see this matches the graph over here. So now that we have a completed sign chart, we can find our solutions using the sign chart. So if I look at the first polynomial inequality over here, this is where f of x is strictly less than 0. Well, being strictly less than 0 tells us f of x is negative, entirely negative. So where does that happen? Well, it happens in the first interval, -4 to -2. Okay, and we write it like so. So this is an open interval with round brackets because we want to exclude the values -4 and -2. Why do we do that? Because it's strictly less than 0. And at -4 and -2, f of x equals 0. So we want to exclude them by writing round brackets. Or we have another interval between 2 and 5, which gives us this interval 2 to 5. Or finally, we have another interval over here, which we write like so. So we can't write the words or over here. What we do instead is use the proper mathematical notation, which is the union symbol, which you can think of as or. So in your test or your exam, make sure to write down the proper mathematical union symbol over here, and your solution there is in green. So at this point, I would urge you to pause the video and have a go at finding the solutions for these 4 inequalities, and then play the video to see the solutions. So the solutions for these 4 inequalities are as follows. So we can see we've made use of the square brackets. Why? Because we want to include the values -4 and -2. And we include them because this is where f of x is less than or equal to 0. And where do they equal 0? At x equals -4 and -2. Now you'll also notice wherever there is an infinity symbol that we've used, we always use rounded brackets because infinity is not a real number. So for example 1, we're asked to solve this inequality over here. So our first step is to make the right-hand side of the inequality be equal to 0. And we do that by subtracting 20 from both sides. So subtracting 20 from the right-hand side gives me 0. Subtracting 20 from the left-hand side gives me minus 14 here. And these two terms remain the same. Now that we have the right-hand side of the inequality being equal to 0, we can move on to step 2. And step 2 is to let f of x equal the left-hand side. So f of x equals x squared plus 5x minus 14. So we have f of x is strictly less than 0. So this is the general form for the first case that we had in our previous slide. So now, for carry on with step 2, we want to find the real zeros of f of x, i.e. find the solutions to f of x equals 0. So now, when we set it equal to 0, we know this is a quadratic, we factorize to give us this, and we solve this to give us the solutions, or the real zeros, x equals minus 7 and x equals 2. So now that we have the real zeros of f of x, we move on to step 3 to producing the sign chart for f of x. So we have our x-axis, we'll input our real zeros minus 7 and 2, and then we'll need some test values to help us decide what signs should go in which interval. So in this first interval here, which is less than minus 7, I've picked the value minus 8. And you can pick any value you want as long as it's less than minus 7. And we substitute this into this function over here. And we end up with a positive value, and we indicate that with a positive sign. Then we pick another value between minus 7 and 2 for this interval. I've picked x equals 0. And I substitute into here, which will give me a negative sign. And then for this interval here, I've picked x equals 3. And I substitute this into here, which will give me a positive value. So I write this with a positive sign. So now that we've completed the sign chart, we move on to step 4, which is to find the solution for this original inequality that we had. Now, if you recall, f of x is strictly less than 0. So this is where f of x is entirely negative. We look at our sign chart. Where is f of x, or which interval is entirely negative? Well, it's only this one between minus 7 and 2. So our solution is the open interval minus 7, 2. If we were to graph f of x, the graph would look something like this. And you can see our solution agrees with this because between minus 7 and 2, you can see f of x is below the x-axis, which is entirely negative. Now, to summarize what we've learned so far, we have 4 steps for the general rule for solving polynomial inequalities. So we have step 1, which is to rewrite the inequality by making the right-hand side equal to 0. And then step 2, to let f of x equal the left-hand side. And then solve f of x equals 0 to find the real zeros of f of x. Then step 3, we mark the zeros of f of x on a number line, and we make a sign chart by testing one x value in each interval. Then step 4, we use the sign chart to determine the intervals you need. And if there's more than one interval, the union of these intervals is the solution. Now it's your turn to have a go at solving this polynomial inequality. I suggest you pause the video and check the solutions after you've done that. So the solutions are this over here, and you can see the steps that we've taken to arrive to this solution. So we've completed our first learning objective, and we'll now be moving on to solving rational inequalities. So moving on to rational inequalities, if you can remember that a polynomial function can change signs only at its real zeros. So what we have here is a rational function where f of x is equal to a polynomial a of x over the polynomial b of x, where b of x, which is in the denominator, cannot equal 0. So a rational function can change signs at its real zeros, where a of x equals 0, or at its points of discontinuity, where b of x equals 0. So it's important that we must include the zeros of a of x and b of x. So now if we look at a graph of a rational function f of x, notice the intervals on which f of x is entirely positive or negative. So we'll highlight the real zero first, and that can be found from solving a of x equals 0. Then we have these vertical asymptotes at x equals minus 2 and at x equals 2. Now these are points of discontinuity, which can be found by solving b of x equals 0. So if we start from the left-hand side, we have this section in red here, which is below the x-axis, so f of x is entirely negative. Then we have the asymptote, and then this section here in blue is entirely positive because it lies above the x-axis, and we can see a sign change that's occurred at this point of discontinuity. So it's gone from negative to being positive. And then if you go further, we have the real zero here where f of x equals 0, and then this section f of x is entirely negative. Then we have another point of discontinuity or vertical asymptote. We can see that this graph or this section of the graph is entirely positive because it lies above the x-axis. So with rational functions, we just have to make sure we understand that sign changes occur at real zeros or at points of discontinuity. So in example 2, we'll be solving this rational inequality. And like before, step 1, we make the right-hand side 0. And we do this by subtracting 3 from both sides to give us this. So the right-hand side is 0, but on the left-hand side, we have two terms. We need this to be a single rational expression. And we do that by having common denominators. So we have x minus 2 over here, and we want 3 to have a denominator of x minus 2. And we change that by multiplying the 3 by x minus 2 over x minus 2. So now to simplify this, we multiply 3 with the numerator over here, and that'll give us this. 3x minus 6 at the top. Now that the denominators are the same, I can simplify the numerator to give me this. And on the right hand side I have 0, and on the left hand side we have a single rational expression. So now that step 1 is complete, where the right hand side is equal to 0 and the left hand side we have a single rational term, we can move on to step 2, which is to make the left hand side of this inequality equal to f of x, like so. So then we'll have f of x, which is this bit on the left, is less than or equal to 0. And this information we're going to use in step 4. That's why I've highlighted it there. So once we've done that, we will factorize the numerator and the denominator separately. So if I factorize the numerator, we'll end up with x plus 1, x minus 5, and the denominator can't be factorized, so we leave it as x minus 2. So now that they're factorized, what we'll do is we'll set the numerator equal to 0, like so. We solve this to give us x equals minus 1, x equals 5, and these are the real zeros of the function f of x. And then we'll set the denominator to 0, and if we solve this, we get x equals 2, which is a point of discontinuity for f of x. So now that we've found the real zeros of f of x and a point of discontinuity there, we're going to move on to step 3, which is to produce a sign chart. So we make our number line like so, and then we input these x values on our number line. So we have x equals minus 1, 2, and 5. Now we need to make sure we write down what they are. So this is the real zero for the function f of x. At x equals 2 is undefined, and at x equals 5 we have another real zero. This will help us later on with our solution. So now we'll find our test values. So in our first interval between minus 1 and negative infinity, I've picked the value x equals minus 2. If I substitute this into the function f of x, I end up with a negative value, so I indicate this with a negative sign. And then I pick another value between minus 1 and 2, so I've picked x equals 0. And when I substitute this into the function f of x, we get a positive value, so we write a positive sign. And between 2 and 5, I've picked the value x equals 3. If I substitute this into f of x, we end up with another negative value, so I indicate this with a negative sign. And in the final interval between 5 and positive infinity, I've picked the value x equals 6. And we substitute this value into the function f of x, and that'll give us another positive sign. And now we have a completed sign chart. So we can move on to step 4, which is to find the solution of the original inequality. So now if you recall, we want f of x being less than or equal to 0. So where does that happen? Which intervals does that happen in? When we look at our sign chart, we can see it happens here and there. So for the first interval, I write it like so. So you can see a round bracket for negative infinity because infinity is not a real number. But remember, it's less than or equal to 0. So we need to include a square bracket here so that we include minus 1. And that's our first interval done. And we want the union symbol because there's another interval involved between 2 and 5. And we indicate it like so. Now we have a round bracket at 2 because it's undefined here, so I can't actually include the value 2, so we keep a rounded bracket there. Now 5 is a real 0 because we want it less than or equal to 0, we must have a square bracket here so that we do include the 5 there. And then if we graph our function f of x, you can see our solutions here matches with what the graph is over here. Now, the general rule for solving rational inequalities can be summarized in 4 steps. So step 1, we rewrite the inequality with a single rational expression on the left-hand side and 0 on the right-hand side. For step 2, we let f of x equal to the left-hand side. So we have a polynomial a of x in the numerator and a polynomial b of x in the denominator. And then we set a of x equal to 0, which is the numerator, to find the real zeros of f of x. And we set b of x equal to 0 to find the discontinuities of f of x. Then we move on to step 3 by marking these zeros and undefined points on a number line. Once we've done that, we make a sign chart by testing one x value in each interval. And then moving on to step 4, we use the sign chart to determine the intervals you need. And if there's more than one interval, the union of these intervals is the solution. So for the second task, now it's your turn to solve this rational inequality. So I suggest you pause the video and then play it once you're ready to see the solutions. And the solution is over here, and these are the steps that we took to get to our solution.